Welcome to The Explainer. I am so incredibly pumped you're joining me today, because we're about to unpack a math concept that honestly governs so much of our everyday lives. Seriously, it's everywhere. To kick things off, let's jump right into a real-world scenario. I want you to picture a sprawling orchard, just rows and rows of trees, totally heavy with ripe apples. Now imagine a team of farmers getting ready to start the harvest. For our purposes today, we're going to measure exactly how long it takes them to pick every single apple in that entire orchard.
So what happens when more farmers show up to pick those apples? I want you to just trust your gut for a second. If we start with just a couple of people, and then we keep adding more and more workers to the job, what actually happens to the total time needed to clear the whole orchard? Just take a quick second to guess. Does that time go up? Does it stay exactly the same? Or does it go down?
Well, if you guessed it goes down, you hit the nail on the head. When we bring in more farmers, it takes proportionately less time to get the job done. I mean, as the workforce goes up, the time taken goes down. It's pretty much just simple common sense, right? But what's really fantastic about this is that this super everyday scenario perfectly primes us for a massive core concept in mathematics.
Okay, let's dive right into this. In our grade 7 math toolkit, we actually have a very formal name for this exact kind of push and pull relationship. We call it being inversely proportional. It basically means that when one variable increases, like say our number of farmers, the other variable decreases, like our time. But hey, the absolutely crucial thing you need to take away from this is that very last part. They decrease proportionally. That means they are changing at the exact same rate.
Let's actually ground this with a concrete example so it's super clear. If you double the amount of farmers, like let's say you go from 2 workers up to 4, the time it takes won't just go down by some random arbitrary amount. No way. It will get cut exactly in half, because the change happens at the exact same rate. Doubling one side perfectly halves the other side. It's like a perfectly balanced seesaw.
And we can totally scale this up to really see the power of this rule. Imagine we brought in a massive crew, say 20 times as many farmers as we originally started with. Well, predictably, it would take exactly 20 times less time to pick all those apples. It doesn't matter how huge the numbers get, the relationship holds completely true.
Now, what's genuinely fascinating is how we can visualize this whole thing. When you translate this concept onto a chart, inverse relationships will literally always create this very distinct downward sloping curve. If you have just 2 farmers, you get this really tall bar representing a huge chunk of time. But man, jump over to 5 farmers and that time bar shrinks drastically. The variables are just constantly pushing against each other, creating that signature downward slope.
If you were reading this trend on a standard graph, you'd trace it out kind of like this. You'd start way up at the extreme top left, which corresponds to having only a few farmers taking a really, really long time. Then, as you move down and to the right along that curve, you're tracking the change. The number of farmers is getting bigger because we're moving right, and the time taken is getting smaller because we're moving down, eventually bringing us to that extreme bottom right.
All right, let's shift gears and see how this builds from a visual idea into an actual algebraic equation. We're moving from the physical orchard straight into algebra, and it takes 2 really specific steps. Step 1 is just writing out the proportional relationship. Saying time is inversely proportional to farmers is the exact same as writing that time, represented by a t, is proportional to 1 over the number of farmers, which is f. But actually scratch that. We can't do actual math with a proportional sign. So step 2 is swapping that proportional sign into a rock-solid equal sign. And to make that mathematically legal, we have to introduce a constant, which we represent with the letter k sitting right on top of that fraction.
Okay, let's demystify this mysterious letter k that just crashed the party. We call this the constant of proportionality. It's basically the specific number we plug into our equation to replace the proportional sign with an equal sign. Now, you might be wondering, what number is k, actually? Well, its exact value depends entirely on the specific real-world relationship we're looking at. It could be 0.4, it could be 100. It completely changes depending on things like the size of our orchard and how fast our specific farmers can pick.
So for our specific apple orchard scenario today, let's just say we've done all the background math, we timed our absolute fastest pickers, and we have our constant. It's 8. That is our magic number, our constant of proportionality for this specific harvest. So we take that 8, we plug it into the top right, exactly where our k used to be, and just look at what we've built, the orchard equation. T equals 8 divided by f. With this locked in, we don't have to guess or rely on our gut feelings anymore. We now have an incredibly precise mathematical tool ready to be used to predict the future of our harvest, based purely on exactly how many workers show up that morning.
Let's actually put this equation to work right now. Imagine it's early morning, the sun is just coming up, and only 2 farmers clock in. So our F equals 2. We plug that 2 right into our equation, giving us 8 divided by 2. You do this simple division, and bam, we can perfectly predict it'll take them exactly 4 hours to finish picking all those apples.
But let's contrast this, right? What if a few more arrive? Let's test it out with 5 farmers. We swap the F for a 5. Now our equation is T equals 8 divided by 5. The result? 1.6 hours. Boom! We literally just proved our initial common sense intuition using solid grade 7 math. More farmers means drastically less time.
So the absolute most crucial point here is knowing how to spot this stuff out in the wild. There are really 2 key ways to recognize an inversely proportional relationship. Visually, you're always looking for that distinct downward slope, a curve sweeping from the top left down to the bottom right. Algebraically, though, you're looking for a fraction format, something like y equals 2 over x. Basically, one variable equals some constant number over the other variable.
Now, before we wrap up, I want to leave you with a bit of a provocative thought to really challenge your new understanding. Think about this equation. 3y equals 5 over x. Notice there's a 3 lingering right next to the y now. So, is it still inversely proportional? What do you think? Well, according to the mathematical rules, it absolutely is. It honestly doesn't matter if there are other numbers hanging out next to our variables. As long as one variable is fundamentally equal to something over the other variable, the inverse rule still completely stands. So next time you're looking at some data, ask yourself, as one thing goes up, does the other come down at the exact same rate? If so, you might just be looking at inverse proportion. Thanks so much for learning with me today, and keep questioning everything.